So far, we've been thinking about how the properties of a gas are related to one another. Now let's think about how the individual molecules are moving about their container. They can strike the walls of the container, and the force with which they strike results in the pressure that we measure. Now, moving about also means those molecules have a kinetic energy, and this we can explore further with something called the kinetic molecular theory. Kinetic molecular theory assumes the presence of an ideal gas, whether an individual gas or a mixture of gases. But it goes farther by considering the motion of the atoms or molecules. It assumes that there is a distribution of kinetic energy in the gas sample. This means that not all the atoms or molecules have the same kinetic energy, but it presumes that there is an average kinetic energy. This is sometimes called the thermal energy of the gas. That name is significant since the average kinetic energy or thermal energy depends only on the temperature. It doesn't matter what the identity of the gas is. The quantitative relationship can be expressed as 3/2 RT. Notice that 3/2 and R are both constants, so we can see the temperature dependence. The conclusion to draw is that if we have two materials at the same temperature, they have the same thermal energy or the same average kinetic energy. You may also be familiar with a relationship from physics that relates the kinetic energy of an individual object to the velocity. Ke equals 1/2 mv squared. Chemists will often talk about the speed instead of velocity. Velocity is a vector quantity that has a magnitude and a direction. Since our bulk gas sample has molecules moving in all different directions, only the magnitude or the speed is of interest for us. Speed can be related to temperature as well. As the temperature of a sample of gas increases, the kinetic energy of the individual particles, and therefore the average kinetic energy, increases. That also means the speed of the individual particles, and therefore the average speed, increases. Here is a figure from a different textbook. On the y-axis is the relative number of molecules. On the x-axis is the molecular speed. The orange curve is for dioxygen gas at room temperature. First, notice that there is a distribution of speeds and thus a distribution of kinetic energies. The most prevalent speed is about 400 meters per second. If you think about track and field in the Olympics, a normal track is 400 meters. Going around that in 1 second is mighty fast, but that is a typical speed for the dioxygen molecules you are breathing in right now. But notice what happens when the temperature is increased to 1000 degrees C, as shown by the blue curve. There is a broader distribution of speeds and thus kinetic energies. Also, the maximum of the curve is shifted to higher speeds. The take-home message is that as temperature increases, the speed and kinetic energy of the gas increases. But there is one more point to make. Consider two gas samples, one with heavy molecules and one with light molecules at the same temperature. And let's bring back our two kinetic energy relationships. If they are at the same temperature, they must have the same average kinetic energy. But they don't have the same speed. If the kinetic energy is the same, the sample with the larger mass must have a smaller speed. M and V are on the same side of the second equation, inversely proportional. If Ke stays constant, as M gets greater, V must get smaller. Heavier molecules will have a slower speed. This is somewhat hard to demonstrate, but take a look at the next video and consider the results.